Hello, ladies and gentlemen. So it's back to physics and away from history, just for the time being, since I've been thinking a bit more about my quantum gravity notion and how to go about proving it. Since I entered into a discussion with a physics professor once, physics professor from King's College London, I won't mention his name, but he was trying to say, because he had a look over my ideas, that, well, it produces no testable predictions. And really, I should have come up with a better answer to his objection then, because I'd already been thinking about the testable predictions of my hypothesis. I was going to say things like, well, closed timelike curves can't be possible, and wormholes can't be possible, and time travel can't be possible, and definitely shouldn't be possible. I mean, if time travel were possible, like if one person were to go back in time once and do anything meaningful there, it would just cause chaos. It would cause chaos down the line somehow. It just would. There would be like a butterfly effect of consequences. If one medieval peasant saw you in like modern clothes, just appearing in a field or something, looking at an iPhone, they'd be like, and then knock-on effect, it would cause chaos, and you'd arrive back in the, I don't know, the smoking ruin of whatever year you'd come from, and just be like, what? It's obviously all your fault for having time travelled. So there's a very thorny bit of physics involved in all this, because we know about things in quantum mechanics like quantum tunnelling and particles appearing to move instantaneously from one position to another, and that's incredibly well documented, and it's the reason, for instance, why touchscreen phones work and all this sort of stuff. So the natural argument in a sort of unification model between general relativity and quantum mechanics, since a closed time-like curve is part of general relativity, is saying something like, well, I suppose a closed time-like curve sort of allows quantum tunneling, or that quantum tunneling is affected via a closed time-like curve. And then we're into all this sort of Juan Maldacena ER equals EPR paradox sort of thinking, which is a tiny bit problematic, because if closed time-like curves existed in their general relativistic formulation, and if wormholes existed in likewise in the same formalism, then we'd be able to have instantaneous messaging, we'd be able to have teleportation, etc., faster than light travel, but then this runs into deep quantum mechanical issues, such as Bell's inequalities, and the fact that we need to construct no messaging theorems. We can't have instantaneous transmission of information, for much the same reason that we can't have time travel. So, so what would I submit in an argument attempting to fuse relativistic thinking and quantum mechanical thinking? I would have said something of the nature that the distance to which one can tunnel in space is predicated upon or determined by the mass of a particle. So particles of a very high mass can teleport further than particles of lower masses. So electrons, generally speaking, tunnel not that far. But theoretically, well, there's always that's the other thing, there's always a probability that the electron could tunnel to any point within, on an infinite range. It never goes down to exactly zero, the probability. And that's actually sort of what my gravity model relies upon. So, yeah, but yeah, the creation of closed time-like curves and reliably being able to send particles back in time so it would be omitted from my model. However, having said that, yeah, the parsimony there would be with quantum tunneling. But we do quantum tunneling all the time, and we don't call it a closed time-like curve. So, you know, this is like so many people are attached to general relativity because it seems to allow things like faster than light travel. It seems to allow cool science fiction stuff like wormholes, and everyone's like, yeah, this is amazing, or time travel. It's like, you don't want any of that shit. Not really. Not in physics, you don't. Alright, keep it in science fiction, but leave it out of physics, for goodness sake. And it comes down to, you know, this Minkowskian space-time stuff, and physics has moved on a pretty long way since then, and we talk about things like anti-de Sitter spaces more now, I think, and these other forms of space. Like, you don't want any of that shit. Like, a curvy space-time, like, the universe is not a trampoline, okay, I don't think. It's not, you know, there's more subtlety going on here. Was my model basically gravitational fields are big clouds of electrons? It's more or less an ether theory with a few subtle additions, or a few more subtleties than that. But I mean, there's a long tradition of ether models, you know, culminating in that of James Clerk Maxwell, and yeah, we have also quite good reasons for thinking that gravitational fields, yeah, are corpuscular in nature, or rather to say are quantum in nature, or formed of quanta. It's, you know, it would be very, very inelegant, would it not? And really quite strange. If you're saying like a gravitational field in one respect results from the curvature of this mysterious substance called space-time, and that objects fall into it, like you have a ball on a rubber sheet and an object moving around it, and it falls into the space-time, and that's one element of it. But then, there's a bolt-on to that. To keep galaxies together, we need different particles like axions, or weakly interacting massive particles, or massive compact halo objects, keeping galaxies together. And we just need to keep adding stuff in, bolting stuff on to make this work. And then you've got like a sort of a cobbled together, not particularly beautiful or elegant universe with big clouds of particles floating around in galaxies, just keeping it all together, and they seem to be there pretty arbitrarily. And then it's like, well, we need to explain the accelerating expansion of the universe somehow, so we need dark energy. So we do this thing now where space seems to, which it seems to do in fairness, produces energy and moves itself apart, and that's more elegant, I think. But yeah. Yeah, yeah, dark energy is more elegant than dark matter, certainly. No, all the stuff that seems to possibly be allowable in general relativity, CTCs, wormholes, Einstein-Rosen bridges, i.e. is what they're called. Yeah, no, you don't want that. That's a problem. It's not a good thing. And like, I know, like, proper physicists will be like straining themselves and thinking like, you're nerds. You want science fiction realities. Think of the problems that could be caused by that. You don't really want it, honestly. No offense to nerds. Nerds are wonderful, but you know, reality's better. If you sent one particle to the past, anywhere in the past, I reckon you just create havoc somehow. You know, you might, I don't know what it could lead to. Something bad. I just think, you know. So yeah, Does quantum tunneling take place via a CTC though? It transports a particle not to a different point in time, but to a different point in space. But then we're talking about space-time, and you know, time here, or here, is a little bit different to time here, isn't it? It's not exactly the same time. I mean, for instance, clocks in Oxford famously run 5 minutes slower than they do in London, and everything's set to Oxford time, which sort of proves a good point. So, you know, my finger here is slightly closer to the, you know, the Greenwich National Observatory, which the international date line and so on, than my finger here, unless London's that way, which I'm not so certain, or if it's that way, because I can't be bothered to figure out where London is in relation to, but you see what I mean. So yeah, I mean, to travel in space is to travel in time. But, so yeah, I mean, we can teleport quantum things with some reliability. Oh geez, I'm probably going to go back on myself, aren't I? So, like, the quantum teleportation of subatomic particles goes on all the time. And what largely interferes with a particle's ability to be quantumly teleported is quantum decoherence, i.e. interference caused by other quantum particles. So if we're trying to transport something very large, then we might have to get rid of Bell's inequalities and no messaging theorems. No? Or wouldn't we? And is this ER equals EPR stuff correct? And an entangled state of two particles represents a wormhole of information, I guess a photon being transmitted between two electrons in an entangled state, whereby, you know, the photon changes the spin of one electron, and that's transmitted instantaneously through wherever to change the spin of the other electron. I guess that's how entanglement works, isn't it? And like the general relativity way of looking at that is to say, well, it's a CTC, it's a wormhole. And the quantum mechanical way of looking at it is to say, but it's a superposition of two quantum states. It's an entanglement, it's an entangled system. And it's, in a sense, it's like these two different theoretical modes of approaching similar things are talking in a different language about the same phenomena. Yeah. Physics is peculiar. So yeah, I mean, my model couldn't obviously rest on proving that entanglement couldn't exist. So I sort of shot myself in the foot in this video by, you know, trying to raise it. Oh, like wormholes, oh, they couldn't be real. No. They don't need to time travel though, they lead to space travel, I think. And you can't go back in time, not meaningfully, I don't think. You know, the past is gone, the future doesn't exist, there's just the eternal now, which is very new agey and hippie-ish to sort of say, but whatever. Yeah. And has like also nothing much to do with like gravitational fields being made of tunneling electrons. And how do you test for that idea specifically? Try and excite the gravitational field and make it kick out some electrons. Big particle accelerator. Detect neutrino winds around the sun, which shouldn't be there. I have come up with one or two other ideas of testing it, I think. Yeah. Okay, thank you everyone for watching. Bye bye.